Hello, programming languages students. Welcome back to our second and probably final Turing machine video. Um, in this video, we're going to go over a specific example, the a to the n, b to the n example here. And so the concept is we have a Turing machine that's pointing at a piece of tape, and it's pointing at the start of a string of a's and b's, and it could be potentially infinite. And we're developing an algorithm to be able to count and make sure that there are the same number of a's as b's, and that all the a's come first and then all the b's come. So a to the n, b to the n. Um, and so what this looks like, how do we actually convert this into a Turing machine? How do we actually make this happen? Well, we define these rules, so we think about what these rules are going to be, how to solve the problem. Um, and then we have to figure out how to draw these rules as a state machine, something that looks a lot like an automata. So in this version of the automata, we actually need three things. In the old version, we just needed a letter, and where do we go with that letter? Now we need the letter or the value we're looking for. We're going to replace that value in memory with a new piece of data. It might be the same one, but we're replacing it. And then we move to the right or left in our memory, in our infinite piece of tape. So let's see what it looks like. So we look over here. Some things look very automata-like, and some things do not. um, let's say we start in state Q0. If we see an A, then we're going to replace it with an X and move our tape head to the right. So again, we're looking at a piece of tape. If we see A at the piece of memory we're looking at, so if the string starts with an A, we replace that A with an X, and then we move to the next piece of memory. In addition, we move from state Q0 to Q1. In state Q1, if we see an A, we replace it with an A, so we basically leave it alone and move the tape head to the right. And also, if we see a Y, we replace it with a Y and move the tape head to the right. So the reason for this you'll see as we kind of work through our example, but mostly right now I just want you to see these are what the rules look like. Given that we read the value on the left, there's a semicolon, we replace it with the value to the right of the semicolon, and then we put a direction for the tape head, either right or left. So the last thing I want to mention is that we have a little empty box down here. This is the null terminating character, so this means we're out of things to check. And I guess the last thing I should highlight is that just like automata, if we are in state Q0 and we try to transition out, if we read in a value that is not A or not Y, which are the two out arrows here, so let's say we read in a B while we're in state Q0, there's no arrow out of Q0 that has a B as the first value here, right? There's nothing that reads in a B. There's also nothing that reads in an X, right? We either read in an A or a Y to continue. If we read in anything else, a B, an X, a Z, a Q, an empty square, whatever, we go to a trap state, just like we would in automata. So if there's not a transition for a specific input symbol and we read that input symbol, we're trapped. And so that will not pass. I guess that's the last thing I should mention. So let's dive in. Let's do an actual example here. So this is what things might look like. We have this tape. It's infinite. It has squares that go off in infinitely in either direction. But we are pointing to an A at the start of the tape. And in this example, we have 4 A's and 4 B's. So we're going to show and prove that this algorithm works and that we can correctly detect that there are A to the n, where n is 4 A's, and the same number of B's. So we start. We're pointing at an A, and we're also pointing at Q0. So we read in from our tape. So we read in an A. That means in our next step, we are going to replace, or I guess as we transition to our next step, we're going to replace this A with an X. We're going to move our tape head to the right, and we're going to be moving to state Q1. So 3 things happened. We replaced the A with an X, we moved the tape head to the right, and we transitioned to state Q1. So let me click. And so I've represented that. We've replaced the A with an X, we've moved our tape head here, and we've moved to state Q1. So again, 3 things happen. So now we're in state Q1. We're pointing at an A. Therefore, we read an A in. And if we're in Q1 and we read an A in, what happens? Well, there's an out arc here that has an A, and it says that we loop back in, we leave the tape as an A, and then we move the tape head to the right. So at the end of this, we're going to still be in Q1, but and we're still going to have an A here, but we're just going to move our tape head one to the right. And so that's all that changed. So now we read in another A. We stay in state Q1, we leave that A alone, we move to the right. Okay, we read in another A. That means we stay in state Q1, we replace the A with an A, we move the tape head to the right. So same thing, nothing happens. Now our tape head is pointing at a B. So from Q1, what happens when we see a B? Well, we are now going to transition to state Q2, and along the way, we will replace this B with a Y and move the tape head to the left. So we've moved to state Q2, we've replaced the tape head, the value there with a Y, and we've moved to the left. So from state Q2, if we have an A, we leave it as an A, and we move to the left. So we're pointing at an A, we leave it as an A, we move to the left. Again, we're pointing at an A, leave it as an A, move to the left. Pointing at an A, leave it as an A, move to the left. Now we have an X. So when we're in state Q2 and we find an X, we replace it with an X, so we leave it alone and we move to the right. And the key here is that now we're going to move ourselves to state Q0. So this is the state where we get to replace A's with X's. So we left it alone, we moved back to the right. So basically what we've done is we've bounced, we found an A, replaced it with an X, found a B, replaced it with a Y, bounced back to the beginning, and then came back over to the next A. So we're going to replace this A with an X and move our tape head to the right, all while transitioning to state Q1. So we now have a new X, and we're in state Q1. We're pointing at the next A in our line. Well, from state Q1, if we get an A or we get a Y, we're going to replace it with itself and move to the right. So we found an A, leave it alone, move to the right. Found an A, leave it alone, move to the right. Found a Y, leave it alone, move to the right. Well, now we find a B. And so when we find a B, we're going to replace it with a Y and transition to state Q2. So we've done that. We found the B, replaced it with a Y, and now we're in state Q2. From state Q2, anytime we find a Y or an A, we move back to the left. So let's bounce on back. Leave Y alone, leave the A alone, leave the A alone, and now we hit an X. Well, when we find an X, we leave it as X, but move to the right, and transition to state Q0. From state Q0, we replace the A with an X, and we're back to this state where we're going to loop over to our B's. Oh, whoops, I guess my slide, I didn't set, I guess at this point I'm kind of saying we follow this pattern. We find the B, replace it with a Y, so we loop back to the B. When we find it, we replace it with a Y and move back to the left. Move all the way back till we find an X. Once we find the X, we bounce back to the A, right? So this is the same pattern we've been doing. We're basically going down to a B, replace it with a Y. Go back, find an A, replace it with an X. Then go back, find a B, replace it with a Y, right? So we're bouncing back and forth at this point, going pretty quick. And now, this is the important part that I'll walk us through. So we've replaced the last A, and we've replaced the last B. When we do that, we're in state Q2, right? That's when we replace our last B. B is replaced with a Y, and we move to the left. And so for every A or Y, we keep moving left until we hit our X. So now we're pointing at our X. What happens? Well, we replace the X with an X, we move to the right. Now we are pointing to a Y. So instead of transitioning up to state Q1, we're going to leave the Y alone, move to the right, and transition to state Q3. So we find all the rest of the Ys, and then as long as there are no more B's remaining, right? If there was another B out here, then from state Q3, if we ran into another B, we'd go off to a trap state. But as long as we make it to the end of our string, to our null terminating character here, without seeing another B, well, then we made it. We transitioned to the right and we are accepted. We're done. So we showed that AAAA, BBBB would be accepted. It's also a really good exercise to make sure that this works and doesn't accept bad strings, to try AAB or ABB and follow the patterns. So that's the idea behind the Turing machine. That's kind of the concept for how it works. We have an input that's a tape that isn't blank, an output, a tape that isn't blank, and then a function is Turing computable if there's a Turing machine that computes it. And so it's a kind of a question to you, and the other Turing machine reading helps answer this, is what functions do you think are Turing computable? What can Turing machines solve? What can they not solve? Um, so I'll leave you to the other reading to figure that out. Really quickly, I'm going to talk about a couple other potential problem solving problems that you can solve with Turing machines, give you a couple examples in the slides. And then, like I said, there's one kind of Turing machine you have to draw, and then there's one actual Turing machine you have to draw for the assignments. Um, so maybe this kind of logic would help. So let's do a number problem. Let's see if the Turing machine can compute any x plus any y. Well, if we represent the x and the y by a series of ones, so x maybe let's say if x is 2, then we put two ones together, right? It's called unary. Um, if x was 100, you'd have 100 ones together. And then we have infinite tape, so we're not worried about this. And then y is represented the same way with a 0 in between. Then you've represented an x and a y as two separate values in your memory. So 2 plus 2 could start by being represented like this. And you could represent any two values, x's and y's, whatever you would like. And so by the time you're done, all you have to do to show that your Turing machine works is solve it such that the tape head points to the start of a 1, 1, 1, 1, 0. So it's like you basically have kind of moved the 0 to the end, and now we've added together x and y. So 2 plus 2 equals 4, because at the end of this, we are pointing to 1, 2, 3, 4. So here's an example Turing machine. And by the way, this is an extremely helpful tool, and I strongly recommend pulling JFlat back out and clicking Turing machine, and it'll help you draw this. And the really nice thing is that when you're done, if you draw this correctly, you can have it show what your input was, what your output is, and whether you accept it or not. And so you can verify that what you did solved the problem you wanted it to solve. And so JFlap can be really helpful here. There's a couple instructions about how you can run and test here and in the slides. Um, and so using the Turing machine option, you can run and test. You select Turing machine from the starting menu, you draw your Turing machine, and then under input, you select multiple run with transducer. Transducer is that infinite tape. And then you can enter your test values. So I enter a series of inputs. I'm adding 2 and 2, I'm adding 3 and 2, I'm adding 4 and 2, I'm adding 1 and 6, and I should get out 4, 5, 6, and 7 as answers. And so you can see this works. Really all I did here was replace the 0 with a 1 and then add a 0 at the end and then move back to the start. And so we've added numbers together. We could write a Turing machine that solves x times 2. So start with a read-write head at the beginning of a string of ones, replace every one with an x, and then slowly find the rightmost x, replace it with a 1, and that means that we go to the first blank and write a 1, and repeat until there are no more x's. And so we end up with a string of ones. And so that's what this would look like. And by the way, x times 2 from the number world is the same thing as copying a string in our world, right? We take a number and we copy it. We'll put them together and now it's 2 times that number. Same as a string. So this is not only times 2, but also just a copier. So Turing machines are capable of copying strings of any length that you want. You have an infinite tape, you can copy an infinite string. Um, so let's see. Yeah, so there's a couple other ways you could copy strings of zeros and ones rather than just ones. And so it gets a little bit more complicated, but you can definitely do it. And so that's kind of as complicated as the string copy gets. Is instead of a series of ones that you copy, Now you can copy ones and zeros however you'd like by replacing ones with x's and zeros with y's and then setting this up. So all these are Turing machines you can create and test. It's kind of fun to problem solve with this because it turns out it's pretty close to how computers problem solve um, when you really get down to the nitty gritty. And so it's a good skill to have, and Turing machines are just a good thing to know about for a computer scientist. Um, and so there's one more example in here, but basically, if you have any questions, please let me know. I believe that I may have given you this example as one of your problems. So I'll leave it to you to figure this out. It's only, so it's only a couple problems, and I think Turing machines are not too bad once you get into them. It's just the initial sticker shock of how do you convert things. Um, but it's an interesting concept, very useful concept, very practical concept, because it relates very closely to computers, as you will read in the extra Turing machine reading. So, hope you have any. If you have any questions, please let me know, and I will talk to you guys next time.